Very good. So hello everyone. Thank you for coming and welcome to the next lecture in our lecture series. Most of you are new here for this installment of lectures, so I will say just a few words about this lecture series. We are doing adventures through the laws of nature, and here this is what is called hypercube of theoretical physics. It has four important quantities: speed of light, gravitational constant, Planck constant, and this is Boltzmann constant. You can think about this also as number of particles. So at the beginning, we were going with one constant at a time. So quantum mechanics, this means that we're exploring the world where Planck constant is important. Then we did statistical physics. It's when number of particles is important, it's very large. And then we went to special relativity where speed of light is important. After that, we started to make a mixture of things. So there were quantum field theory, waves and quantum light and symmetry. These three lectures were about when speed of light and Planck constant are important at the same time. Starting from last Sunday, we went on to massive direction when gravitational constant is important. We did gravity last Sunday. And today we are going to have another gravity-related lecture, which will be on astronomy and on different aspects of it. And here, on the one side, with gravity is important, the gravitational constant is important, but in reality, it will be a mixture of many different things. There will be part of evolution of universe when the speed of light is important. Stars is balance between gravitational force and quantum mechanics effects. And all this we will hear today from astronomers who actually do real experiments. Many lectures are done by theoretical physicists, so we just write formulas, have no idea what people do in reality. But I'm really excited to hear what is actually happening, and not just by formulas, but real life. So thank you a lot, Anton and Bengt, who are going to speak today. And let's enjoy this event. Yes.
Yes. So thank you very much for the people that have made it here. We're not too many here, so it's a great chance to interact a lot. Just talk to me, interrupt me, ask questions. So my name is Anton Dikeus. I work here at Uppsala with my topic being early universe and the formation of structures in the early universe, and in particular how to model the formation of the first stars, the first galaxies, how to observe them. So my idea for today is to I want to make like a story of this lecture. So we're starting with something quite different, and we're gonna take our perspective towards the early universe and start to build towards it, so you can see a progression of what we're trying to reach. So to begin with, some audience interaction, I'd like to ask, just please yell out, what do you believe that we're actually seeing here in this first picture? Any suggestions? Yes?
Mm-hmm. 3 stripes, the third one is brighter than it has a dot neck, which I believe to be a star.
Wow, that's very good. Yeah, you're perceptive, you're seeing all the details. Do we have more suggestions? So let's say there was a star, we say there, and any more ideas what this can actually be? Yeah? Exactly. Yeah. Closer. Very well be the case. Or a very close image of her genes or something. Close up. No, but actually, I don't think it will be helped even if I zoom in on this picture. It doesn't reveal anything more. But what you're seeing here is actually our home, planet Earth. I just pasted that into the image to hammer it home. But what we're seeing, the image is a picture taken of our planet Earth, taken by the Voyager spacecraft. The picture is taken the year 1990, the 14th of February. So I was born in September that year, so I wasn't born here, but a lot of you were born. You lived on the planet when we took the picture. If you're on the right side of the planet, you're on the picture. So it's a remarkable thing. It's a distance of 6 billion kilometers away from Earth. The spacecraft had passed the point of Saturn, more or less, and they decided when the mission was over that they could use the camera The suggestion came from Carl Sagan, who's a famous popular scientist, or a scientist as well, but he suggested to take the picture of the Earth because it would have a big meaning for us as human beings to actually see this picture. They were a bit hesitant because they knew that that could destroy the camera on the spaceship, because you have to point it back towards Earth and then you would look close to the sun, and that could destroy the camera because the sun is so bright compared to all the other objects. And the beam of light that you perceptibly saw is actually a reflection of sunlight into the camera of the telescope. So that the Earth seems to be suspended in a beam of light, but that's really a reflection that you're seeing there. And a funny fact about this, and we're talking about distances, this is so far away. The photo was taken and was recorded on an old recorder, just a tape recorder, like the ones we knew in the 80s and 90s and so on. So it was recorded on a tape recorder and then transmitted via the Deep Space Network. That's what it's called, and it's still used today to communicate with satellites and space missions. And it took 5 hours for the radio signal to reach Earth again and transmit the picture. So that's how long it takes for the speed of something traveling at the speed of light to arrive, even from this distance. And the world looks tiny, remarkably tiny. And here we met today at Ångström. We're trying to figure out how to look towards the universe and try to look deep and understand more about this vast cosmos that we're actually living in. So meanwhile, here somewhere on Earth, you have the Guyana Space Flight Center. This is the area, or the actual country in the area that launches much of the space telescopes that we're using today. For example, just recently, James Webb Space Telescope, the newest space telescope that we have, was launched from this position. This is a country that's just north of Brazil, so it's in South America. And it's a very neat place to launch missions into deep space because you can use the rotation of the Earth to get an extra speed and out into space. So it's more easy, more fuel economic to launch from there, among other good things. So. But in the center, this Christmas, the James Webb was assembled in its final state and folded up like this. So this is when it's inside one of the houses that you saw in the background there. So it's in one of the clean rooms. There is not supposed to be any dust, any particles, nothing in that room that could pollute anything in the telescope. You cannot have even a particle on the mirror. It's really, really important that you have nothing to disturb the images. It's in a clean room with some people walking around in clean suits and everything in order to not contaminate the telescope. So it's folded up like that in order to fit inside a rocket to be launched. So that's kind of perfect. That will kind of perfectly fit inside a rocket, you know, the long shape that it has. And in space, it looks like this. So this is the James Webb Space Telescope as it would look in space. Yeah. Yeah. It could be something like that, absolutely. But what you see there is actually that you remark the bottom thing here, the pinkish glow, that's the sun shield of the telescope. So that's the part of the telescope that's in the direction of the sun. So these are sun shields that protects the telescopes from the sunlight because it will get too hot and it can disturb the instrument. And the actual science parts of it, that we call it, is up here, the yellow parts. These are hexagonal mirrors. They're coated with gold, real gold. If you take all the gold and collect it, it would be the size of a golf ball. So you have to buy that gold and plate the mirrors. But the mirrors themselves are made of beryllium, the metal beryllium, which is very good for this purpose. So the sunlight comes in here, reflects, the sunlight, the starlight, or whatever light that we're observing comes in, reflects on the primary mirror, the yellow part, goes to the secondary mirror, the thing that you see here, and then it goes into the focus here. And that's where the images go in, and you can record them as an image, or you can take the light and study the light as it goes to some other instrument. On the other part, below here, you have the solar panel that gives the power to the telescope, and you have the communications part that sends signals back to Earth. So you can actually send the data back because this telescope is about 150 million kilometers away from us. It's beyond the moon in an orbit, so it's far away. So you cannot go there. Maybe ever, maybe in the future we can go there. Yeah, question? This is called the James Webb Space Telescope. Yeah, so you can read about that more if you want to. So the reason why I'm talking about this is because this is the telescope that we're using now, want to use now to study the early universe. And it has a very big mirror, so it's 6.5 meters in diameter. It has a very good resolution, so you can see fine details that we want to study in the early universe. We want to see details of objects, and the image here that I show to give you an idea of how good the resolution is if you take a Swedish 5 krona, which is, I don't know why I took that because we don't have them anymore, but they're about 3 centimeters in diameter. And if you take that from here at Uppsala and then place it on top of Globen, the building there, that's in Stockholm, it's an arena. If you place it on top of that, you could be able to resolve the coin from here with the camera. It will be able to resolve that small object. And yeah, so you would see it, but it wouldn't be able to resolve the thing here, the crosses, on the coin. It wouldn't be able to see the details. Then you would have to have better resolution. And that's possible with ground-based telescopes. They actually have a little bit better resolution because they're so large and they can be built in order to have particularly good resolution. But this is remarkably good for a space telescope. For example, the extremely large telescope, which is built right now, can see details that are 100 times smaller. So it would be able to see the different little markings on the coin even. And some more information is that it's very heavy. It's 6 tons. That's not really heavy because it's launched into space, and I mean it's a lot of technology, but only 6 tons. 7,000 moving parts that needs to be assembled in space because you saw that it was folded up. Now it's folded back in space. So it's 7,000 points where it could go wrong, but nothing went wrong. I will just go through this, and I will return to it. No, it's all automated. Everything is run automatically by computer programs that have been pre-programmed by people on Earth before they sent it up, and they tested it many times so that it wouldn't fail. But the size of it is about as big as a tennis court. The wavelength that it observes light in, we'll talk about wavelength a little bit soon, but it observes in the infrared. So there's a wavelength span, and it has near infrared and mid infrared capabilities to observe light. And the cold side of the telescope is about minus 223 degrees Celsius, and the hot side towards the sun is plus 110. There's about 300-degree difference in temperature on the different sides of the telescope. There's a lot of fun facts about that I won't go through. But the infrared light that this telescope is made to observe with is really good to observe the early universe, because the light that comes from the early universe is redshifted, actually, because the universe expands. Light from galaxies and everything in the early universe reaches the infrared. So that's a phenomenon because of the expansion of space. So that's why we're interested in infrared light. But what we think about when we think about infrared light, we're thinking about heat, really. So that's heat radiation, the thing that you feel from the sun. That's the warmth of a light or whatever that you can feel. That's infrared light. And that's heat. And the different areas in the spectrum of light that we can observe, you can see here as just a representation. So on the very left, you have very high energy radiation. Those are gamma rays and X-rays and all that stuff that are a bit dangerous for us if we're not protected. And you have the optical light, which many of our previous telescopes were built to have. They observe in the optical, and that's Hubble Space Telescope, for example. It's been serving us for a long time. But now we see that there's now three space telescopes that are built or being built and sent into space, which will observe in the infrared now. Because that part of the radiation does not reach the Earth, so it gets stuck in the atmosphere and it doesn't go down, so you cannot see it with instruments on the ground. You have to go to space generally. Yeah, question? Yeah, just an ordinary airplane that would actually go up on high altitude, and then it can observe infrared radiation from that altitude because it hasn't been absorbed by the atmosphere at that altitude. So that's why you want to go up there. But I don't know too much about that mission, but it exists. But this is the part of the area that we're looking at now, the infrared. So the Earth atmosphere actually is a big problem when that we just said here. It's a big problem so we need to go to space because the atmosphere would just glow in infrared if we were to observe. Take a infrared camera, and look at the atmosphere, and it would be completely glowing with infrared lights. We couldn't see the stars behind it. And another problem is also turbulence. So if you've ever seen the heat or the tingling of the stars, like in the evening, it's the turbulence in the air that causes small little movements in the atmosphere, and that's a big problem if you want to do detailed images. And perhaps you can see the jiggles here on the picture of the moon, as it's jiggling due to the turbulence in the atmosphere. So you don't want to have this problem when you're observing with infrared light, really. So that's why you rather go to space. And that's also the reason why the telescope has to be cooled down to that cold temperature that I just said, because if it's not that cold, the heat flux or the heat from the telescope itself will ruin the images. So the telescope has to be as cold as possible in order to not ruin its own images. So it's even glowing itself in infrared light if we're not cooling it enough. But when we do that, we get really, really sensitive to this radiation. And we can actually observe the light from an insect, infrared emission from an insect, just an insect like this. This is an infrared camera. If you look at an insect in an infrared camera, you could detect this insect if you were to place it on the moon, the distance of the moon, with this telescope. So you would even be able to distinguish an insect's radiation on that kind of distance. It's so incredibly sensitive to radiation in the infrared. So that's really why we built it with that purpose, to be that sensitive, because we want to see the light from the most distant galaxy. And a galaxy may not be glowing brighter than an insect if it's far away. But we need to have that kind of sensitivity. Yeah, if we were to take the distance to the moon, so from here and take the insect, place it on the moon, and we would be at this distance that we are here, the Earth, and see it, then we could actually see the radiation from it. Okay. I think that's probably the example is really that this is kind of the limit. Yeah, so the moon would be more or less the limit, and if you go further than that, problems, we would get too many problems with that, and disturbances, and there are more complications, of course, but yeah, it's sensitive enough. Yeah. The telescope, if we had it on Earth or in yeah.
So would we be able to see a telescope learn down the moon, or if we look on the telescope?
But it's a good point, because if we're on the Earth, we have too much disturbances, and we couldn't see it. Yeah, so it needs to be in vacuum, in space, and not disturbed by anything, because if we couldn't detect it on Earth because it would be too many disturbances. Yeah. And to return here now to just what we're now that we've actually launched this telescope. It was launched in Christmas Day 2021. So just recently it was launched into space, and it traveled for about a month until it reached its position in space. And until now, still the last month now, it's calibrating itself, the telescope, in order to start taking real images of science cases. So I went through all this talk here to give you an idea of what we're using to observe the early universe. And I will talk about what we're trying to observe and how these objects came about, really. How do they form? What are their characteristics, and what are we looking for, really, with this telescope or other instruments? So the kind of setting is that we were looking up in the night sky. Here we have the Milky Way, as it will be seen in a very dark and clear night. It's a picture taken from somewhere in Canada, where there's not too much light pollution. So you get a clear view, and the band you're seeing here is the Milky Way center. So the center of the Milky Way looks very bright. If you're taking a camera and just point it towards the sky and let it stay for a while, and keep it still and collect the light. So looking into this now, we're zooming in on this haze, on this myriad of objects, looking deep with the James Webb Space Telescope. We would eventually be able to see something like this. So this is where my dramatic side enters, and I needed to enter some dramatic title. This is a quote from Buzz Lightyear from Toy Story. It's my hero. if you've seen Toy Story, you know. But the image that we're seeing here is actually the Hubble Deep Field. So this is already a picture that's taken, and every object that you see on this picture is a galaxy. So it's not a star. There's one star, and the way, as far as I know, there's one star. That's the bright object there, which has these spikes coming out from it. That's a star. You can see that because it has these spikes, and a point-like object, more like a star, would have that, but a galaxy wouldn't. So more or less everything that you see are galaxies at different distances. And what the Hubble Space Telescope did was to look at the darkest area on the sky that it possibly could. So it was not looking into the Milky Way, like I kind of tricked you into thinking maybe, but it's look at the most dark place that it could find, maybe the size of your little fingernail, if you take that and hold it up the sky, and it took a picture of that small area on the sky, and you see this. So it's just full of objects, and this was a bit of a surprise. We could suspect perhaps it would be something like that, but we wouldn't know actually before we took the picture that it would be this remarkably full of objects, and we can actually see them with Hubble. So what we did, what we've done now so far, the most distant objects that we've been looking for in these kind of pictures would be this galaxy that you see here. So this is zoomed in. This is the most distant galaxy that we've ever observed. So it's at a redshift at 11, and that doesn't say say too much to you maybe, but that means that it's in the very epoch of the first objects to form in the universe, and it's at a distance of about 32 billion light years away from us, and it existed 400 million years after the Big Bang. So the redshift tells you how much the light from the object has shifted because of the expansion on its way here. So it's shifted more or less by a factor of 12 in this image. And the blob that you see here is nothing like the galaxy that you would see, like a disk galaxy like the Milky Way or something that you're used to, but it's just a blob of light, very irregular, not as many stars and so on. But it has these irregular shapes. That's generally the case. Yeah, question? That's actually not exactly true if you want to be very specific. I've lost the key here also. But it's not actually 32 billion years. That's what you said, 32 billion years old. No, because the thing is that the universe is only 13.8 billion years old, as we know it. So it wouldn't have time to reach us really, if we're thinking about if it's this far away. But it's the expansion of space that allows it to be that far away. So at the same time as the light has traveled towards us, space has expanded. So it's expanded just enough to be able to travel this kind of distance anyway, though it wouldn't really have time in a static universe that's not expanding. Moreover, that was a galaxy. What we just recently managed to do now is to detect a star at these kind of amazing distances as well. So this is really remarkable. This is work that me and a colleague, Erik Zachrisson, here at Uppsala University was involved in this project. So this is just a recent publication and a recent discovery. So we actually found in the very distant universe a star, a single star, the light from a single star. And you can imagine in the galaxy we just saw, there are maybe 100,000 millions of stars in that galaxy, and all the light combines to show that to provide a galaxy that's visible, that is bright enough. But now we detected one single star. It's probably just one thing. It could be maybe 2 or 3, but it's not more than that, what we believe. And the star is called Arendel. And it's located here at where the arrow points. It's just a little fuzzy little blob here as well. And this object was, the light was emitted from an area which is 28 billion light years away. And it existed 900 million years after the Big Bang. And the way we managed to see that was through gravitational lensing. So there was no way that we could actually observe this object if we wouldn't have gravitational lensing to help us. And you can see that from this is a bent arc here in the image. This red arc that goes here across the image is actually the galaxy, which has been distorted by gravitational lensing into an arc. And the very point where the star was located is the point where maximum magnifications occur. So the star was just boosted by maybe a factor of as high as 4,000 or something. So 4,000 times stronger was the light because this effect, gravitational lensing. So that's one of the tools that we're really happy that the universe provided us with, because without that it would be impossible. Yeah, question? Now you can be anywhere in space as long as you have something between you and the object that can be responsible for this. So it's like if you want to magnify something on a paper, like with a magnifying glass, you would have to put the magnifying glass between your eyes and the paper, right? Then it would magnify the light. In this case, the thing that acts like a lens, like a magnifying lens, is that whole cluster of objects, like a cluster of galaxies. So there's a huge assembly of objects between us and the distant star. And when the light comes and supposedly is supposed to pass through the object, it rather bends around the object because of effects that were calculated by Einstein, general relativity. So that's really comes from his theories. And you can see on some of these objects, the clusters here, the bright spots around here are actually galaxies belonging to the cluster which lensed the objects. Yeah? So they could just easily, if we just naively look at the picture, we would say that those can also be stars. But the thing is that the calculations that we use, so this is all based on magnification calculations. So we have to make a model saying how magnifications like this occur in the system. So you have to trace all the different components of the cluster, like there's a galaxy and a galaxy there and so on, and also dark matter, which I'll talk about a little bit more. So the contribution of dark matter is the major thing that does the lensing. So I could show you a lensing map of this, because you make a really well-established map that tells you that there we get the magnification of 10, maybe here we get 11, here we get 1,000, and so on. And you have a critical line which passes immediately over the, or directly over the star, which is the maximum magnification line, the critical line. So it's almost like what you call it a caustic line. It's the kind of phenomenon that you see if you're looking at a pool in a summer day. If you're at a pool, and you see the reflection of light on the surface of the pool because this jiggles on the water, and you can see the reflections on the bottom of the pool. You can get these bright lines, riddled across the pool floor. These are caustics because of the surface of the water creates caustics where the light is focused maximally. And exactly the same phenomenon happened here, exactly on the star. So we know that it's on the brightest line where it can, or possibly the best place for it to be. It's just luck really for us that it was there. So we know from the image that this is a really, really small object because it's not even resolved into a bigger object. We cannot see any more structure in it. And we would be able to do that if it was a bit bigger. And what always happens is that objects, when it's gravitational lens, they go into being multiple images. So you can see more than one image of the same object because light can take several paths through space towards you, to your eyes. You can go above the cluster, below the cluster, on the sides. So you can get many pictures, but not all of them are as bright. What happened with the star was that both the images actually appear in the same spot. So these are actually, it's split into two, but it was so tiny, the object, that you couldn't see even that it was split into two. And the other objects that you pointed out, those are star clusters. And that's actually the same object. So the left and the right object there are it's the same star cluster, magnified and split into two that went to different paths around the cluster and then was seen. So we can actually tell that this is the same object by studying the light from it. And we will get more details when we do observations with James Webb, because we have time now that we've gotten with the telescope that will be observed this summer. So we will look at this object with the telescope and then confirm all our suspicions, so to speak. So I wouldn't say that we're certain about everything here, but we're quite certain, and we will hope to confirm our suspicions about all this. But I'm open to being wrong as well about parts of it, but it's still quite solid, I would say. To continue, Hubble which we just talked about, barely reaches the epoch of the first galaxies where they formed. So if we're looking at this kind of map here, we are to the very left. Our Milky Way would be to the very left in this picture, looking into the universe. And this is formed like a wedge. So the Big Bang is to the very right, the bright spot there. That's where the Big Bang would happen in space-time. And the furthest galaxy that we've ever observed, I've put that into the diagram, as you can see here, the blob. That's really close to the early universe if you look at this map. It's quite far away. And that's about as far as the Hubble Space Telescope reaches. James Webb, the new telescope, will reach beyond that and even into this area where you see that the dark ages appear. So this is the time in the universe when no stars and galaxies even had formed yet. So it will be able to probe and look at the very, very first star-forming galaxies, and maybe, if we're lucky, even the first stars to form in the universe, because it will be so sensitive that it can reach that. And if we're lucky, once again, to see lensed objects, that will help us even more. And that's about, looking at them, that's about 50 to 100 million years after the Big Bang, if we're looking for the first stars in the universe. But like I just said, we're looking towards the cosmic dark ages, which are there called, dramatically called. And as we try to look closer now, what I will do is go closer to the Big Bang and try to see more about the very first instances where we lead up to the formation of stars and galaxies. So zooming in here, like I pointed out, you see that James Webb, the bottom arrow, really reaches very close to the dark ages, where the first stars just form. But if you want to look closer, you want to understand more about the very first instances of the universe, because that's an interest of many and of mine as well, to understand how can you start with the universe and then evolve, and then you get galaxies and all these shapes and all these kind of distributions of matter and galaxies that we actually have. So when we're trying to reach towards the very earliest instances of the universe, we're getting into trouble, because the Big Bang is actually veiled in a sort of mist. So it's hidden from our eyes. Because if we want to look towards the very right, towards the bright dots, the Big Bang, that's outside of the picture now, we're coming across this cosmic microwave background, which I've put it into the diagram here. And that's actually a radiation that fills our whole sky, and it's the most distant structure that we have ever observed. So I said galaxy was the one I showed you. That was an object, but this is an entity, like something that we observe from the early universe. So that's a cosmic microwave background, and it fills the whole sky. So if you would have a radio transmitter with you, just a simple one, and you would go out and point it towards the sky or wherever, you would get a static noise in your receiver. And that noise is this radiation from the universe. So this is, of course, not what you do with your radio receiver, but this is a high-tech space mission which did this observation. It's a Planck mission that did this. That's a satellite, which was sent out into space, measuring radio waves and microwaves. So this is in the microwave band, but very close to radio waves. And there's a big noise just here. For many people, this was just noise. I mean, it was detected as noise by people working for a telephone company. They wanted to do better transmissions in radio, but it ended up seeing that it was only noise in their measurements. So that they got the Nobel Prize for that, which is quite hilarious. But there was a big discovery. What was that? Yeah, a Nobel Prize for noise. So it doesn't have to. You don't have to have a smart idea. You just have to stumble upon something great, and they actually do. But this is really the light from the Big Bang, and the radiation here was emitted 380,000 years after the Big Bang, and that's really, really close to the Big Bang. I mean, we're talking billions of years otherwise, but now it's only hundred thousands of years. So this is a short time after the Big Bang. And to me and to you, I think this is mostly noise in the picture, but this picture is so rich with information, and it's probably one of the most astonishing discoveries that has given us so much information about the early universe. And I don't think anything has given us more information than this about the universe. That could be argued, but what you do is you look at this picture and you do a statistical analysis, and you see how many of the red dots and the blue dots and how large they are, how are they clustered together, so on and so on and so on. You just crunch your numbers, do statistics on everything, and then you come up with all kinds of stuff that the universe is a geometrically flat universe. It doesn't have a curvature. You can calculate the energy content of it. You can calculate how old the universe is. Almost everything can be calculated from this picture, which is very remarkable. But yeah, to go past that, because that's a point where we reach with radiation, electromagnetic radiation, just the light. I will go back there, but this is what you see, and you cannot go beyond that, because anything earlier in the universe than that is just hidden, because you cannot look through this maze or this mist of radiation, because everything in the universe was ionized. It was a plasma at that point. So if you want to take radiation that's supposed to be able to go through all this from the very first instances of the Big Bang, it's just impossible, because it will interact with everything that's in this plasma. So you cannot see beyond it with electromagnetic radiation. But there are hopes, or I would always see it as an inevitability that we will be able to go through this with gravitational radiation, for example, which is a big thing now that we've made a big steps forward in gravitational wave radiation and the way that can be detected as well. So in quite near future, we will be able to look through this perhaps, but how we will do it and what information we can get remains to be seen. But just to go to the earliest instances now, and I will not, there's not any detail here. This is not my home field. I mean, I guess Dimitri, you would be glad to tell us more about how space-time works and how you can generate particles from nothing and so on. But I will just hand-wavingly tell you that the universe, for my purposes, started out as an arbitrary quantum fluctuation. So just space pops out into existence, and it comes from a sort of foam or a quantum fluctuating space-time. So space and time can fluctuate and come into existence from nothing, more or less, in this framework. There are, of course, many problems with that and how to explain all that, but it's perfectly plausible that quantum mechanics, the theory about all the small things in the universe, can actually allow for a universe to pop into existence like this. And you're taking something that's nothing and you're creating the whole universe. Of course, then you think you're creating an immense amount of energy in this sort of this sort of happening that the universe creates from nothing. But actually, if you're looking at this in detail, you can find that the energy doesn't have to just pop into existence, because it can cancel itself. There's symmetries that cancel it. So you have negative energy, or actually gravitational potential energy is negative when we're looking at the total energy of the system. So the potential energy can be shown, you can relate it, and you can actually create the universe from nothing, theoretically. But there are caveats to this, of course. But going from there, let's say that the universe pops into existence and it starts to form particles. So from there, the universe, it's immensely hot. So it's incredibly hot, so billions and billions and billions of degrees. And from this, particles come out. So the analogy would be that something like water droplets condensing out of a water vapor. So you can see here like water droplets forming on the window screen because it gets cold and they create a water droplet from the steam. Similarly, because it goes through a phase transition from a gas into a liquid. And in a similar analogy, from the very high energy content of the early universe, there's so much energy stored in the quantum fields in the early universe, the particles begin to condense out of this energy field as it cools. So when it's too hot, it's not possible to form particles because every particle will just be destroyed and behave more like radiation and heat. But as it gets a bit colder all the time, because it starts to expand, it cool because of the expansion. The energy going down, or the heat going down, really, and temperature going down, means that you can actually form some particles out of this. So this is how we find that we can actually create something from this energy. This pure energy creates particles. So just a fraction of a second after the Big Bang, the universe has reached temperatures where protons and neutrons begin to form. So these fundamental particles that we know, familiar with now, that we can study, actually formed just fractions of a second after the Big Bang. So at that time, the temperature was low enough to form these protons and neutrons because they were not destroyed by all the strong radiation. I mean, if you take a proton, it's built up by quarks. And if you take that and you smash in high energy radiation into them, they can just rip them apart again and they will be destroyed and you will get no protons. But if it gets cold enough, it will start to form protons and neutrons. So after about a minute, there's 7 protons for each neutron in the universe. And this is important because it's more protons than it is neutrons. And this tiny difference in the proton mass and in relation to the neutron mass, there's just about 0.1%. That makes sure that you get 7 protons and 1 neutron, because it's more probable for a proton to form because it needs a little bit less energy to form. So you form 7 instead of 1 neutron. And this, I would say, we can thank a whole existence for this. Because if you would form exactly the same number of protons and neutrons, what would happen eventually is they would begin to merge and they would form helium. So if you would have just as much neutrons and protons, you would form only helium in the universe, and you wouldn't have a single hydrogen atom, perhaps. And we all know how hydrogen is so abundant and so important for our lives. What then we'll talk about stellar evolution and so on. Almost the whole theory, every framework is built upon the face of hydrogen burning in stars. So everything that we know about stars in their whole lifetimes, everything is based on the fact that hydrogen is the most abundant element. And if we would have been unlucky, this would not be the case, and we would just have helium. And helium is not a very useful gas. It's a noble gas. It doesn't interact with anything. It couldn't form water. It couldn't form much at all. So that wouldn't have been a very nice universe, but it could actually evolve and form heavier elements then, but we wouldn't have any hydrogen. And that would be a problem. No, let's say the laws of physics governs this, because some sort in the basic laws of physics says how much heavier the proton is, or the neutron is, or the proton, and that decides in part how this ratio would become, but also the temperature at which these formations become inefficient. So the universe expands and cools, and at some point the interactions which makes protons and neutrons becomes too slow, and it can't happen anymore, and that's why this abundance kind of freezes in. So you get this number, and then the rest of the universe, I will tell you a little bit more what unfolds after that. But I mean, if there was if there would have been a difference in the heat or so on, and temperature and so on, you could perhaps form a different ratio, but it would probably be something similar. But then what goes on is that it's so hot still that fusion will happen. So just the process that happens in stars and in a fusion reactor, if we could build one, or in a hydrogen bomb, for example, the kind of interactions which has so much energy where you fuse hydrogen atoms into helium, that occurs in the early universe because it's still hot enough for this to happen. So what happens then is that all these protons and neutrons begin to be swallowed up in these kind of processes and start to be forming large amounts of helium. And because there are 7 protons and 1 neutron, and this process is very efficient at this time in the universe. So all the neutrons are swallowed up and form helium. So all neutrons end up in helium, or maybe in the element it's called deuterium, which is heavy hydrogen. That's just a proton and a neutron, but that's a type of hydrogen, or an isotope of hydrogen, so to speak. So we form all the helium and all the hydrogen in the universe. And what happens is that we get, in mass fractions, you get 75% hydrogen and 25% helium in the universe. And that's the starting point. These are the elements that we start the universe with, and that we can start forming stars with. So this is what we can start with when we're trying to look forward to the formation of stars and galaxies and so on. And I think I'm going to have to speed up a little bit through this because we had a bunch of questions, and I think so I had to take a bit more time. But I'm going to skip forward to show you some of the important parts that I believe here, in order to not drag this out too long. But the universe continues to cool from this state. What happens then is that it's cooling and it's cooling and cooling, and has the hydrogen and the helium content, but it's still ionized because it's too hot for electrons to bind to atoms. So there's no real atoms as we know them because they don't have any electrons with them. So it's like it's still ionized. That's like a flash of lightning. Yes, the air is ionized in a lightning flash like this. And when the universe becomes cold enough, in order to the electrons bind to their atoms or to their protons or helium nuclei, you can begin to form neutral atoms. And that's exactly what happened when this radiation was emitted. So that we just talked about, this radiation that filled the whole universe, the plasma. When the electron started to bind to their atoms, the universe became transparent and the light was emitted, reaching us eventually today. So this is the radiation that was emitted at that point. We're gonna have to save the questions until after. You can ask more then, so we can manage to make more progress here. But this is the Dark Ages, and at this point you have these large-scale structure. What you have really now is no light in the Dark Ages, but you have still some sort of structure. And this, what you see here in the picture, is dark matter. So this is not luminous matter. It's just represented as being luminous, so you can look at it. But this is really a web of dark matter. And this is some exotic particles that we don't know too much about, which actually make out the majority of the universe's matter content. And this has also been observed by observatories, that the universe also looks like this web structure. It follows this dark matter structure like this. So this is actual observations of every single point here is a galaxy observed. So you actually, when you start to observe far into the universe, you actually see this web-like structure as well that starts to form. What I'm going for here is actually to understand how eventually gas starts to fall into and form the structures of galaxies and so on. So this is just some simulations that show you how first the web structure, and now you see how gas, actually real gas, fall into these objects, and they look different than the web structure, but it starts to fall into the structures that we have with dark matter. So these are real simulations that are done in pure physics, really. No mumbo jumbo, no animations, real physics that represents everything that we see here. So now we're seeing actual stellar light, the way we see a galaxy. So this is just simulated. This is not a real picture, but this is a simulation of what physics would tell us would happen if we would just let the simulations do the job. And now they're zooming back out to see, that was a galaxy that you saw there. The size, the scale there, the size. It's zooming out to see the bigger picture here of large-scale structure. And you can see here also the dynamics that happens in the universe here and forming objects here. So that was the velocity of different gases inside of this structure here. So that could be from exploding stars and so on. So I won't go into too much detail. I think I will leave it to you, Bengt, to actually talk about stellar formation and more about that. I will just try to summarize a little bit going into that, I would say. Just ending here is that when we have these abundances, the different that we are talking about, the hydrogen and the helium, we have tiny amounts of lithium. Those are the only elements that we start with. And from this, we start to build the stars and the galaxies that we try to observe now. So in the early universe, there was only these elements, and it was really hard to form stars. So Bengt will talk about more about star formation that we know about in the local universe and understand much better. But in the early universe, gas only had hydrogen and helium. And what that meant was that there was very few ways for gas to collapse and cool. So in order to collapse, gas has to radiate away energy. And the only way to lose energy in space is to radiate it. So here on Earth, we can lose energy by putting our hand on a table or like put it in cold water or something. We can conduct heat away from us. But in space, you cannot conduct heat anyway because there's vacuum around gas and so on. So you have to just radiate it away. But that's really hard for the primordial gas, for the helium and the hydrogen, because they have so few ways of cooling. They're not molecules, and none of these elements are very prone to have a lot of energetic transitions where you can lose energy. So there's a big problem and stuff that we're working on right now to try to model how this happens and how stars can actually form. Anyway, when we only have hydrogen and helium. So these are the star forming areas which Bengt will talk about. These are nebula. So this is an actual picture of a nebula. This is a star forming region. And if you were to be able to go from this dilute gas in the universe to something dense like these kind of dense gas clouds, they would be quite cold and they would be quite dense. And in some areas in these nebula, you get actual star formation stars. Because in order to form a star, you have to maybe be able to condense all the gas and collapse it to become very dense and compact. And the only way to do it is to lose energy and form a quite cold environment. But in the center of the environment where the actual star is born, or the very densest parts of these clouds, you can actually get fusion starting once again. And this is more, Bengt will talk about this more. But the first generation of stars, this is things that I've been working on. We hope to be able to observe them with James Webb, and if we can, there will be a big part of understanding these puzzles all the way back to the very first instances of the universe. So we can actually put pieces together with the puzzle. Like we want to observe the first stars, and then we can understand more about how the universe was just after the dark ages, and just try to take all the small steps towards the early universe and understand more of where we come from. So I will just end there, and I will leave more to Bengt. I have my ending slide here. Going back to Earth to take and think a little bit about what we've achieved here on Earth. I mean, all us people in this little pale blue dot here has managed to do conceive of all these ideas, do these all instruments, and try to understand what we are and where we come from. And the way I see it, we have 6,000 years of recorded history. That's not very long in these grand scales, and we're already on the verge of answering ancient questions like where did the universe come from? How was the universe formed? So it's quite remarkable what we've achieved. We're living really now in an age where new eyes are open on the cosmos. So we're getting new instruments like James Webb, and we're getting a lot of new technology coming up all the time, which actually it's a great time to be alive in order to do these great discoveries that will be appearing quite soon, the way I see it. So to end this, I say long live curiosity. Thank you for your time, and may peace rule this world. Some questions? Yeah, absolutely. Feel free. Yeah. Like the web. Yeah, the web structure. This filamentary. Yeah. Well, it's a natural phenomena from it happens naturally from the simulations, at least. So it's hard to conceive, like to actually calculate from some sort of, you start with a single equation and you want to derive that kind of thing, but you have to let a system of freely interacting particles, like in this case galaxies and stars, to just evolve and see what you form. So it's kind of similar, like I don't know, throwing up a can of water into the air, and maybe you can form these little filaments, the way when it can actually it settles into place. So they've done experiments, so you can actually achieve web-like structures with just random phenomena. But the actual laws of physics, the simulations that I showed, they result in these kind of structures as well. And it's these kind of tendencies that, especially for dark matter, which is very different from normal matter, and doesn't interact at all with each other. So it has the tendency to form these kind of filamentary structures, and that's kind of, it doesn't really behave like normal matter would, really. But other than that, I think to our best knowledge is really the simulations at this time. Yeah, dark matter would. Yeah. Yeah. It would definitely. Yeah. yeah, it wouldn't form. Of course, I wouldn't rule out that say that ordinary matter could form in the way it does. But just like I said with the picture on this microwave background, if you do a simulation and you have all your physics and you say that we have this much dark matter and it should behave like this, and it only has gravity and it doesn't interact with light and so on, and you let the simulation go, and then you study the whole distribution, then you can measure how clumpy is it, how big are the voids that there's no objects at all in, how many filaments do you get inside a certain size of a box, and all that kind of stuff. And if you take normal matter only, you don't get anything like what we're observing, because it doesn't behave at all like that. But you have to have dark matter to reproduce anything at all like that, what we're seeing. But there's still like small subtleties that we haven't resolved. But still, dark matter and dark energy, which I didn't talk about, there's also a big component of the universe. But if you use them, you can reproduce what we see very well. So I would say that's the way we understand this, kind of the best way that we have right now. It's that we cannot reproduce what we're seeing if we're not doing dark matter. It's impossible, really. It's not impossible. I just get this in my head. I hear these other people. I hope so, of course. There are people that are trying to explain it without it, but it's the main idea. The paradigm is dark matter. But there are subtleties. I haven't detected any dark matter yet, any particle of it, but experiments are working with that as well to find dark matter. Yeah.
You said that the total energy of the universe was 0 or about 0.
Mm-hmm.
Is that dependent on there being dark energy or just negative?
Yeah, that's definitely one component, and I would gladly pass it over to someone that's really knowledgeable. This is not my field, but let's say to understand a little bit, dark energy is absolutely necessary for the expanding universe, the way it expands, the way it does. We have the early epochs of the universe, was also a part called inflation, where the whole universe just expands immensely fast from this very early state, early dense state. And without dark energy, it's really hard to understand why everything would move. It's impossible to understand how anything could move apart when gravity is attractive. So when it's moving away from each other physically, it has to be some sort of conversion of energy into some sort of energy field, which is dark energy then. And it's proposed that it's vacuum energy. It's in the energy of the vacuum itself, in space-time itself, and so on. Because otherwise things would naturally just fall back towards each other, and it wouldn't expand the way it does. But dark energy is completely taken over and pushing the expansion. It's pushing things apart. So there's definitely an interplay here with like the total energy of the universe, the energy body, whether you can equal. But whether or not it's increasing with time, or if it's the same constant or decreasing, and so on, that's an open question.
Okay, so let's go to the break, and we will come back at 10 minutes to 7. And during break, you're welcome to ask any questions to Anton and also Ben. So they can ask any questions you want, and also you can ask me. Don't ask me about astronomy though, but probably I can talk with anything else.
Yeah.
So you're welcome. Feel free to ask any questions now. The break.
Mm-hmm.
Yeah. So now we have Ben. We're going to speak about evolution of stars in periodic table.
Thank you.
Yeah.
Yes, my talk is a bit more traditional than Anton's very nice presentation before. Now, so my name is Bengt Edvardsson. I work here at Ångström Lab, Department of Physics and Astronomy, just as Anton. And the title of my talk is Stars and Galactic History. And like Anton, I like you to ask questions while I'm talking, because I know these things very well, and I may think that things are very easy, simple, but there are always questions that you can race. So please don't be afraid to ask. So I have a plan to continue after Anton's presentation here. I'll start where Anton left us with after the first stars. We'll talk a bit of star formation, atoms and atomic nuclei, which are very important for stars. Atoms in stars. How do we know that there are atoms in stars actually? And the spectral analysis. We analyze the light of stars, which is actually the way that we do know this. And to do the research I do to understand the buildup of the chemical elements in the Milky Way galaxy and in the universe, we choose our stars particularly in a particular way so that we can get the information we need. And then I'll talk a little bit more about star formation and how stars shine, where their energy comes from, and then what they end up with, what the products are at the end of a stellar life, what they contribute to the galaxy. And in the end, we are all made of stardust, as you may have heard. So after the Big Bang, this is what we had in the periodic system, periodic table. Mendel's periodic table. We have hydrogen. Anton told us we had 75% hydrogen and 25% helium. But I'd say 90% hydrogen and 10% helium, because I count the number of atoms and not the mass of the atoms. The helium atom is 4 times heavier, approximately, than a hydrogen atom. So that was sometimes you hear 90-10 for the contributions for hydrogen and helium, and sometimes you had 75-25. So both are right, but they are talking about slightly different things. And then there was a little bit of lithium, the third element in the periodic table. That was what we started, what the first stars started with. They were probably very, very massive and very hot, as Anton told us. They lived their life, and in their deaths, they expelled a lot of elements that had been produced inside the stars. All kinds of atoms, all the periodic table. They distributed atoms of all kinds around them. And this gas, this very hot gas, which was thrown out from these dead stars, they cooled and they mixed with all the hydrogen and helium which was around them. So in astronomy, we have a lot of traditional old words. So we talk about hydrogen, helium, and metals. Everything except hydrogen and helium is called metals, if you talk to an astronomer. So oxygen is the most common metal in the universe, if you talk to an astronomer. It's a kind of funny, but that's a lingo which has followed us since 19th century, actually. And because there was a lot of hydrogen and helium and very few stars, there was a tiny amount of metals in the gas after the first stars were born. And in the gas, you saw in Anton's the simulations that Anton showed us, that there was gas falling into filaments and in clusters and galaxies forming. And that means there were lots of motions in the gas. Also, the explosions from the stars that made the new atoms stirred the gas and made it mix around. It's called turbulence. And some places the density of the gas was a bit higher, and other places the density was lower. And in the denser region, it may be dense enough that the gravity could keep hold of the matter in a certain region, a little bit denser region. And then these regions could contract, the gravity contracted. And if you compress a gas, it gets hot. Everyone who has pumped a bicycle by hand know that the ventile gets very hot. So if you compress a gas, it gets hot, and the gravitational contraction of the gas heats the gas. And the heat increases the pressure and counteracts the contraction. That's why the gas needs to lose energy. It radiates, as Anton told us. It radiates energy away from close to the surface. Heat gets expelled. Infrared radiation gets away in the galaxy from the cloud, and then it can cool again, and then it contracts some more. So this is a process which compresses the gas to make denser gas clouds, which can start forming stars. And heat will always flow from warmer to cooler regions. That's the first law of thermodynamics. Is it the first? Ah, I think so. So the hotter gas in the center, the heat in the center of the gas clouds will all slowly move outwards by radiation or even by boiling or convection, as we call it. When you heat something from below, the hotter matter will rise and the cooler matter will sink down. This is called convection. So energy will come from the inside and go outside, and in the outside it radiates away. And the gas and the cloud can contract even more. The gravity can compress the gas and increase the temperature in the center. Yes, it's infrared and microwave radiation which leaves the cloud. When warm atoms collide with each other, they get excited. The outer electrons can jump up to higher levels, which means that the atom gets, as you say, excited. But an excited atom will always want to go down to the ground level again. And that it does by sending out a photon, light. So this is the way that the hot gas, it collides, it excites the atom or a molecule, and when it goes back to its ground state, it sends away the energy as radiation. So that's how it cools. Yes, when the electron falls back, it emits a photon, gas light. So in this way, the heat is converted to light. And then the contraction can proceed, and the pressure increases. And it gets hotter and hotter and hotter, and the pressure is highest in the center, in the very center of the forming star. This is not a black hole, as it may look like. It's actually a dust cloud in the Milky Way. This needs a push. Something will push it together. If this happens, it may actually contract enough to start forming a star. It contains hydrogen and helium, which is not visible, and then it contains a little bit, 1%, less than a tenth of a percent of the matter is in heavier atoms, like carbon and silicon and iron, etc. That's what blocks the light. It's the dust consists of cigarette smoke, small particles, but it's a very small part of the cloud which actually is the dust. But you can see it blocks the light very efficiently. It's of course enormous cloud also. The dust blocks the light from background stars. And a cloud that is contraction, that means if it had a slight bit of rotation from the beginning, it will start spinning faster. You know that it's the same process as an ice dancer. As an ice dancer who makes a pirouette, it spins faster. So that's what happens when the gas cloud contracts, and the rotation will get faster and faster. But the matter which is close to the equator, close to the equator of the cloud, will stay there because of the rotation, what we call the centrifugal force. Inertia. It will keep some of the gas out, stretched out around the equator. And you form the central star, and a disk of gas and dust around the star. In the center, in the very center, the first nuclear reactions start happening at a few million degrees Celsius only. Some of the lithium, which we saw in the first part, will come out, collide with hydrogen, and will make 2 helium atoms. That will heat the gas, continue to heat the gas in the center. And when the temperature rises up to about 10 million Kelvin, 10 million degrees, about absolute zero, then the hydrogen atoms can start to build up helium atoms. And Anton showed actually the process, and I will talk a little bit more about that later. In the meanwhile, planets and asteroids and comets are formed in this disk of gas and dust. So that's why all the planets in the solar system all rotate in a plane, and they rotate in the same direction. It's a reminiscence of this disk around the equator of the forming sun. These are images of disks around new stars, real images. This is a disk that we see from the edge. So this is the disk. The star is hidden here in the center, and the light from the star is reflected or scattered by some of the dust above and below the disk. And as gas it's still falling into the star, but all of it cannot actually go down to the star. There are magnetic fields, and the rotation is very fast. These magnetic fields spiral around, and they eject some of the gas. As you can see here, this is a gas jet that comes out from the star. And there is another one which you can't see in the other direction. I can't say if it's this way or that way. I mean, it's the axis of rotation is horizontal. Yes, right. But I can't say which direction. Yes, the jet is along the axis of rotation. Exactly. Very good. To the right, we have another example. There's the star, and here is a gas jet which is coming out. You can see from year to year that these come further and further away from the star. You observe it again. Here is another star which has been doing this for a long time. You see at these ends, we have gas that was ejected a long time ago, and now it seems to be ejecting gas in a slightly different directions. So this tells us that this is probably a binary star. It has another star which makes this axis of ejection, the axis of the star, to process exactly. As you can see, if you spin a top, it will process like this. So it's so this is very likely a binary star. Yes, some of the gases is spelled as jets, and strong magnetic fields guide these gas into jets. This is an infrared image of a nearby young star, Beta Pictoris, quite a famous one. And we can see the disk on one side, and on the other side, we see it from the edge here. The star itself is blocked by a coronagraph. And the reason is that it would otherwise be so bright, so it wouldn't see the rest. So it's blocked. But what's happening? There is a forming planet in October, and here it was in November. So these are two images which are superimposed on each other. So here we can see an object where a planet is actually forming together with a star. As time goes, the very strong light from the star will evaporate much of the gas and the dust in the disk, and also wind from the star will push it away. And what remains is the planetary system. And the hydrogen atom, you know, this is the very simplified sketch of an atom. You have the proton in the center of the hydrogen atom, and an electron which goes around. And this electron can only have certain particular orbits. This is the ground level. This is the first excited, second excited, third excited, etc. They are not in reality circular, and they are not in a plane in reality. But this is a sketch to show this. This down here is an excited hydrogen atom. And the negatively charged electron goes around it. And it has only certain orbits. And as I mentioned before, collisions and light may excite the atom and kick it upward to an outer layer, excite the atom, as I mentioned. And the electron will very quickly fall back to the ground level and emit a light, a photon. So that this is the process more in detail. The number of protons determines what kind of element it is. So if you have a proton and one neutron, it's still a hydrogen atom, but it's a heavy hydrogen atom, a deuterium. And the atom works very, very similarly as an ordinary hydrogen atom, but it's twice as heavy, of course. A helium atom has 2 protons and 2 neutrons and 2 electrons. And if you build, when you build heavier atoms, if you merge 4 helium atoms, you will form an oxygen atom, 8 protons, 8 neutrons, and 8 electrons. And because they are in an atom, there are similar numbers, there are the same number of protons and electrons. They are electrically neutral. They don't have any net charge. And if they lose an electron, or if they have an extra electron, they will be called ions. Then they are electrically charged, and they work somewhat differently. A lead atom has 82 protons, 82 electrons. And to keep these protons together, these very positively charged protons, the electrical force will want to kick them apart. These neutrons help to keep the protons together. So you can't make a lead atom with many more or many less, many fewer neutrons. You can have slightly different numbers of neutrons, but not very much. Okay, how do we know that there are atoms in the stars? They are only just colored dots, if you look at them. So the answer is that we have to study their spectrum, in detail. And to do this, we have a telescope. And this is my favorite telescope. It was in Chile, at a mountain in Chile, and I've been observing with it several times. It sends the light to a spectrograph that's diverges the light into rainbow, if you like, into different colors, where we can study in very great detail these spectra. And this is a kind of a childish image, which is meant to show what the spectrograph does. If we start with a moraine, which we put in a big funnel, and then we sift it, we sort it with the fine sand in one side, the gravel in the middle, and the very large stones in the side. It's similar to if we put the light from a star, which consists of all colors, into a telescope. The larger the telescope, the more light you collect, of course. That's why astronomers always will have larger telescopes. So it goes, and here the spectrograph is represented by a glass wedge. It's a simple spectrograph, and it sifts the light just like the sift for gravel. Okay, so we want large telescopes. This is a real spectrograph. It's a bit more complicated than this glass wedge. I'm not going to go into the details here. So, if you have a hydrogen atom in this star, of course, the star contains mainly hydrogen. 90% of the atoms are hydrogen. They it's hot in the gas, they collide. Some of the atoms are excited. And if there comes a blue-green photon of a particular color, and it hits an electron which is in the first excited state, it will kick it to the fourth state. It will kick it to the so-called H-beta line. So it needs this photon, this light particle, needs to have exactly the right color to be able to kick one of the hydrogen atoms up into a higher state. And it will be destroyed. The photon is destroyed and the atom gets excited by light. And this is not only true for hydrogen. Every atom in the periodic table and all molecules have these kind of processes. And you can say that they have their own fingerprints in colors, color fingerprints. And this is a sketch, a spectrum. We usually think of a spectrum as colors distributed from violet to red. And here comes the infrared, which we don't see, and here's the ultraviolet, which we don't see either. And you see some black lines here. These are actually lines which are formed by hydrogen atoms in the stellar atmosphere, or it's an image, of course. Light jumping from the second level to the fourth level will give this a blue-green light. From the second to the third level will give this red light, and so on. So this pattern of dark lines will tell us exactly that it's hydrogen that we are seeing here. And in daily life, we don't look at the spectrum in color like this. We make a tracing, we measure accurately how much light is coming at different colors. And we show it like a tracing like this. The light intensity here and the wavelength, the color of the light on the horizontal axis. These are computer-generated spectra of stars. They all have exactly the same chemical composition. The difference is the temperatures of the stars. So the hottest stars are at the top, about 10, 20, maybe up to 100,000 kelvins. And the coolest stars is perhaps around 3,000 kelvins. And you see that the spectra look very different because depending on the temperature of the star. In these cool stars down here, the M stars, it's cool enough that lots of molecules can form. In the hotter stars, the temperature is so high, so molecules are destroyed by collisions all the time. So we don't have the molecules in the hotter stars. And here is a famous slide for us who are a little bit older. Remember the light on the motorways, the highways, it was yellow. And that was because they used the sodium lights, sodium lamps. But then we instead of having it in absorption, we had it in emission. The lamps were giving out only this yellow light. And you see there are examples of several atoms here. CH, magnesium hydride, titanium oxide, cyanide, not very nice things. But you can see that there are lines, millions and millions of lines actually, in a stellar spectrum. And we can use each of them to determine the abundance of chemical elements, how much there is of different elements. Because with a computer, we can simulate the production of these spectra in a stellar, from a stellar model, the stellar model atmosphere. Many stars preserve their birth gas at their surfaces. So the sun, if you look at the surface of the sun, it has approximately the same composition as the gas had where and when it was formed in the Milky Way. So it's a perfect sample of the gas in the Milky Way when the star was born. And many stars can live very, very long. Many stars can get older than the universe. So there are stars which are very, very old, which we can see today in the Milky Way. And the motions of the stars, they give us clues to where the star was formed in the galaxy. They have orbits in the galaxy, and we can use that to calculate with the gravitational potential of the galaxy where the stars is likely to have been formed. So with this, we can observe well-selected stars, and we can map the amount of chemical elements at different times and different places in the galaxy. This is called nowadays galactic archaeology. So we are digging up old matter from different times and different places in the Milky Way, and we can make a puzzle together, a picture of how the chemical elements in the galaxy have. Sometimes, yes, when a planet is moving around the star will have a slight motion, which you can see as the spectrum of the lines moving back and forth as the planet is going this way and the other way, because they're moving around each other. Sometimes the planet also comes in front of the star and makes it darker. So you get, for a little while, the star is not so bright any longer. Then it comes back to the right. So, but that's not the spectrum. That's a total light when you measure the whole light. But spectral lines move because of the planets. They rock the planets. Stop. Yes.
And it still can understand.
Yes, certainly, because different spectral lines have different sensitivity to magnetic fields. And when the planet moves, the star, all the lines move the same. So it's a very unison thing. So this is the cloud which may one day form a star. The temperature in there is only 20 to 30 Kelvin above the absolute zero. You have 90% hydrogen atoms, and the hydrogen is in the molecular form in this cold temperature. So it's H2 gas, and 10% helium, or 25 if you talk down. And then a small amount of metals, which forms dust. Gravitation keeps the cloud together. A push from some way may start a contraction, and rotation is inevitable. It will start rotating, and you will see the disks forming around it. When the star is forming, you will find a disk around it. And the energy comes from gravitation. When you bind particles together, you can get out the energy in form of light or heat. So it's gravitational energy which heats the gas. Oh, I already showed this. Sorry. Hydrogen becomes helium and energy. That's during most of a star's life, they will get energy from converting hydrogen to helium. The temperature is about 10 million Kelvin, and 4 hydrogen nuclei will successively form a helium nucleus. There we have the protons, and here we have the helium. To do this, 2 of the protons have to be changed into neutrons. And this is called used by the weak nuclear force. A proton is converted to a neutron plus positive electron, so-called positron, and a neutrino, a very weakly interacting particle, which we have heard been able to measure for perhaps 30 or 40 years. So the hydrogen atoms, they make energy, they make the positrons, which immediately find an electron and annihilate, also gives photons converted to light. You get a helium nucleus, and you get these two neutrinos, which actually comes out from the center, and which we can measure on the sun. It's kind of a thermometer of the temperature in the center of the sun. It's about 15 million Kelvin. So light and medium mass stars. The sun is a little bit more than a little bit overweight stars. I mean, not really the average star, a little more massive than most stars. And during almost all its life, it gets its energy, its heat, its light comes from hydrogen fusion. When the hydrogen is out in the center, then there will be only almost helium in the core. The core consists of almost pure helium in the very center of the star, and some electrons, of course. And then you have, instead of having 7 particles, you convert that to 3 particles, and that means that the core of the star can contract even more, and the temperature can rise even higher. And when it's about 100 million Kelvin, then 3 alpha particles, 3 helium atoms can, if they come together very, very similar time, they can form a carbon nucleus. So this is called the triple alpha process. And that is the next energy step. That will happen to the sun when it has burnt its hydrogen in the center, and it's become a red giant star in approximately 5 billion years, about twice as long as its age now. For a massive star, they can continue to build up heavier and heavier elements. So this is a supergiant star, a star with perhaps 20 solar masses, 20 times as large as the sun. A supergiant, you can see it swells up and becomes as large as it almost swallows Jupiter in its orbit. And it's extremely thin gas in the surface. But in the very small center, you have like an onion shell structure of different burning stages. It's hottest in the center, there you can have so-called silicon burning, which makes iron. And further out, you can build up elements from helium to eventually iron. And this iron core, you cannot get any more energy from fusing iron. You need more energy. If you want to merge 2 iron atoms, you need more energy. You need to put in energy. You don't gain anything. So this is the end. The iron core will only grow and grow and grow and grow until it gets so massive that the gravitation will make it collapse. The iron core will collapse. Then all the iron will be, the temperature is so high, so all the iron atoms will be crushed by the photons, by the light, into helium nuclei. And the helium nuclei will be crushed, so they have protons and electrons. And in the end, the pressure gets so high, so the electrons are pushed into the protons. That means that you will have only neutrons in the when the collapses end. And then the matter gets extremely stiff. It stops. It's called a nuclear bounce, a core bounce. The collapse stops, and it sends an enormous shock wave out through the other gas, the outside gas, which is falling after, and lifts the gas out from this core. And also, when you push an electron into a proton, you will make a neutrino, one of these very light particles. And those will actually help to push the gas from the core, from the infalling gas out in the stars, out into the interstellar medium. And the elements which are formed in these outer shells, they will be thrown out into the interstellar medium. And of course, there are lots of other elements than just those are mentioned here. There are all kinds of elements in here. And also the energy helps to build heavier nuclei. These stars are very unusual. the massive star, the more massive a star is, the more unusual it is. But this, yeah. Sorry,
This kind of fusion shell is 10,000 kilometers. It's helium. Before helium. So it's about 10,000 kilometers where you have this.
Yes, it's a very, very tiny part of this enormous bloated supergiant star. Yes, it's very small. I don't have the numbers, but the core is very dense and hot. I can't verify that right now.
There's also the sun doesn't have this kind of fusion process at all.
It has hydrogen to helium, only what is in the outermost. This is the hydrogen fusing shell.
I mean, isn't that true, like, that the sun-like star wouldn't go all this way?
No, certainly. It's only the massive stars which do this. Yes, the density is probably not so high in the sun as it would be in here, because the gravitational is also very hot. When you compress the matter, the gravitation is very hot. And it's the electron degeneracy which actually holds the pressure, the degenerate electrons in the gas.
Describe was the formation of a neutron star, right?
Yes.
And that's so the iron core, the element is of the iron, and the iron is crushed on its own gravity.
Yeah. Yes.
And the helium and protons.
And neutrons eventually. Yes. And then it may also be that the core it bounces and then it continues to collapse to a black hole.
Yeah.
Yeah. Yes. And on the chemical composition and rotation and other details. It's very complicated to make a computer supernova. So these stars have very, very short lifetimes. The iron core collapses, the outer layers are expelled. This is the famous Crab Nebula, which exploded in 1054, I think. Was viewed by Chinese astronomers, a new star in the Taurus constellation. It was visible on the day for a few days, for a few weeks, apparently, they mentioned. And now we can see it expanding from year to year. And if you actually take pictures several years apart and you calculate backwards, you arrive in the beginning, in the middle of the 10th century, 11th century, sorry. So this is exactly what they saw. Heavy atoms form. It will be bright as a galaxy for a few days. And you get a remnant neutron star or a black hole and this expanding gas shell, which will continue to mix with the other gas and enable the formation of the next generation stars with somewhat more chemical elements. And if you want to be an alchemist, you should have, for instance, an iron core and 141 neutrons. And you push all these neutrons into the iron nucleus directly, and then 53 of them will decay to electrons and electron neutrinos, an antineutrino actually, and you will have a gold atom. So this is what the alchemists would have needed to do in order to make gold. I think they were quite a bit far from success. So, and if you see what these massive supernova are making, you can see it's quite a lot of the elements in the chemical, in the periodic table. Very many of these elements are made in these kinds of stars. And those stars become red giant stars, as the sun will be. You may have seen Arcturus. If you see the Big Dipper here, recognize it? And you follow the tail or the handle, you see the bright red star Arcturus, which is a red giant star. It's probably similar to what the sun will be in 5 billion years or something. And it's approaching the end of its energy producing life. And in the end, it will not explode as a supernova. Most stars will not explode as supernova. They will instead blow out their outer layers in a strong wind. This is an example of this. It's a planetary nebula, the Ring Nebula, it's called. It's one of the most famous planetary nebulae. It's gas very expanding from the wind expanding from this dying star. In the center, you have a white dwarf star. It's barely visible here, which emits enormously hot ultraviolet light. And that makes the gas shine. That makes the shell visible. It's a UV light from this thing, which makes fluorescence. And this is expanding, and after 10 or 20 or 30,000 years, it will not be visible anymore, and the gas will be mixed with the hydrogen and helium and be able to take part in the next stellar generation. And red giant stars, they make another mixture of elements. For instance, these elements that I've been analyzing in my spectra, barium, etc., are very prominently made in these stars. Some of the carbon and nitrogen also. Certain stars may also become, certain light stars may become supernovae. These are called supernova type 1a. It's a binary star system. They're not so heavy, they live quite long, but one of the stars is probably more heavy than the other one. It evolves first, becomes a red giant, and then a white dwarf, makes a planetary nebula and a white dwarf. And then we have the other star, which starts to become a red giant afterwards. And then some of the gas may fall down on the white dwarf and build up its mass. So if the white dwarf will get heavier than the Chandrasekhar mass, 1.44 solar masses, and then you will have a detonation. It will be a carbon-oxygen fusion bomb, and the whole star will blow into pieces. Another way may be that two white dwarfs actually spiral together. So these are the brightest supernova, and they are very similar to each other, and they are used to study the structure of the universe. Because we know how bright they are. If you measure the brightness, we can tell the distance to them. So they are standard candles, sorry. These type 1a supernova are known to make most of the iron group elements. Of course, they make a lot of other things. And I did this, I was concentrating on this. They do a lot of other stuff also, but mainly, they're mainly the producer of iron group elements. So the iron in us probably comes from supernovae of type 1a. And then there's one more process to make elements. This is called spallation. And this happens to the very lightest elements, lithium, beryllium, and boron. They are so fragile, so they cannot be built in stars because it's too hot. They will be destroyed by the collisions in the high temperature. Instead, they are formed in the gas, in the interstellar medium, in the cool gas of the Milky Way. When a high energy cosmic particle hits a carbon nucleus, it can split into smaller, or an iron nucleus or an oxygen nucleus. It can split into smaller elements. And this is how we think most of the lithium, beryllium, and some of the boron is made nowadays. It's a process called spallation. And as you see, most of the beryllium, much of the lithium today is made this way, and some was made in the Big Bang. Yeah, probably it was made in space, in the vacuum of space. Yeah. Yes, that's the first burning stage. I mean, some of the gas is formed into stars all the time. Much of what happens in the stars is thrown back into the interstellar medium. Some is left into remnants like black holes, neutron stars, and white dwarfs, which will remove atoms from the universe. I don't know if that's an answer. I'm afraid I don't really understand the question. No, but well, some of the elements are locked up into stellar remnants, but there is only about 1% of the matter in the galaxy which is now formed into heavier elements so far. So there is a lot of hydrogen and helium left to form stars. You mean that will be so rarefied? But yes, I guess the stars in the Milky Way will die, and no more stars will form eventually. I guess, yeah.
The peak of star formation in the universe is not long. So when the most stars formed in the universe was a very long time ago. So we're declining now. Less and less stars are forming.
Yeah.
Generally.
Okay. So if you put all these together, you will find a colorful periodic system table. So the different elements are made in different processes in the galaxy and in the Big Bang. And we are all made of these elements from different kinds of stars and processes in the universe. Here on Earth, the atoms have all their electrons. Water is liquid, and complex molecules can form with these low, nice temperatures. And they can develop almost infinitely. And they have made us, for instance. So my final point is that astronomical objects are extremely simple compared to the very simplest living cell, actually. So we are doing the easy science in this university. All the other stuff is more difficult, I think. Thank you for listening. Are there more questions? You know that two massive objects going around each other, they will move around that common center of mass. So this is the center of mass then, and they will continue dancing around the center of mass altogether. And if we are looking at it from this side, here is our eye. We're looking at the light. We have a spectrograph. We look at the spectrum. Here, the planet, the star. This is this is planet, and this is a star. We only see the light from the star. The planet is very faint. But this time, the star is moving away from us, and this makes the whole spectrum shift to the red. So the spectral lines move to the right, And when we see the star going this way later, when they have changed places, then the light will be blue shifted. So all these spectral lines will move back and forth. Doppler, exactly, it's a Doppler effect.
So check it. The center of mass is based.
Yes, yes.
Okay. So
It's extremely small. That's why it took so long time to find the first planet. It was only in the late 90s with a very, very accurate and stable spectrograph they were able to see these tiny shifts. It's moving faster, yes. But the star is 10 million times brighter than the planet. You wouldn't see the sun if you went to another star. You wouldn't see the Earth.
what I mean is the spectrum of the star.
Yes, yes. But that's all we see
Yeah.
because this is so faint. The planet is so faint. Right.
So you can appreciate resolution with their measurement.
Yeah.
It just is crazy.
So it's just you start to build spectrographs now which can measure a centimeter per second. That's incredible compared to the speed of light. What the motions of 1 centimeter per second. That's absolutely amazing. And actually, our Professor Nikolai Piskunov here at the astronomy department is working with such instruments. He's a spectrograph constructor. Yeah.
I have a question. So the first generation stars, do we have white dwarfs now from the first generation?
We don't know really what they were. People think that they had to be very, very massive.
Oh,
And those stars, yes. I mean, there should be a distribution of some kind. So perhaps there may be white dwarfs which are left from that time, but we have not found them yet.
the majority are massive.
That's the assumption. That's what you are looking for. Very, very bright stars.
Yeah, it's one of the main parameters in any model is that varies distribution of masses. It's not known.
So this star you showed us, it was first generation star, right?
Yeah.
Second,
What did you mean?
The star, morning star.
That one. It's not unknown right now. We can hope that it could be a first generation, but it's likely not, because the galaxy that it belongs to is a little bit enriched with metals, but not very much. So it could be maybe the second generation.
So even so, it's even still second.
Maybe, but if we're lucky, it's the first generation. But
you may get spectra to see if there are other atoms.
yeah. So we'll get the spectrum like this on that star and see if it contains anything other than helium and if it doesn't, then we get a nice paper from that.
Trying, yeah.
Yeah.
Very short.
Lifetime, the massive stars. Yeah. Few million years. That's nothing in cosmological. Yes. They form and then they die. Yeah.
Yes, please.
No, our lives are infinitesimal. But you can do a lot of things during your lifetime, I'm sure.
Spallation was heavier nuclei is crushed into this
by protons and alpha particles, which are emitted in for instance, supernova waves or Wolf-Rayet stars, etc. We measure those coming to the Earth, these cosmic rays, and we can see them. Make these yeah.
Also one source that could happen.
For boron, I think. Yeah.
And then they will also have gamma rays.
Yeah, yeah. You mean the cosmic rays? Yeah. Right. Yeah.
When we can get
Yes, you make hydrogen to helium, helium to carbon and oxygen. You jump those. Yes. Beryllium 8 lives for a very, very tiny fraction because the third alpha particle comes and makes carbon. It's very, very unstable. So the three particles have to come almost at the same time to make carbon atom.
very improbable different carbon.
Yes, but there are many atoms. But what we can say is that the same amount of energy comes from each outside the core. The same amount of energy comes from one layer to the next. And the temperature is higher in the center, which means that the photons are more energy rich. They are more ultraviolet, gamma ray, X-ray and gamma ray. So in the center, you have gamma radiation, but at the surface, it has been degraded to infrared or visible light, what we see. So they are converted all the time. They are emitted and absorbed, emitted and absorbed, emitted and absorbed. And the energy goes slowly out, getting colder and colder. The light gets cooler and cooler.
So let's things back again. Yeah. Before we finish, I would like to make a small announcement about what is happening. If you will ever get them. Yeah. Almost. So we have a good summary now, right?
Yeah. In reverse.
Big Bang. Yes.
No.
Okay. So in the lecture series, we have 2 more lectures left. The one is called Theory of Everything. It will be this Sunday. So it's me who will be speaking, and it will be in Stockholm. You can come there in person, or you can join by Zoom. So I'm a theoretician. This means I will not tell you about big and very precise measurements. Well, I can claim that we have gigabyte-long formulas. But mostly I will speak about something else. I want to speak about attempts of physicists to reconcile all these constants together into one theory. So this is quite exciting. We do not have the answer yet. This is a slide lecture. It's view into future. We will stop speaking about what we know. We'll speak about what we do not know and want to find. And the last lecture will be next Friday here in this room. It will be by a professor in biophysics. It will be about physics of life. It's a very different approach, both to astronomy and both to theoretical physics. So I'm also very excited to see how it will go. And it's kind of curious how would argument that biophysics come after theory of everything. Well, honest answer, the lecturer could make it that day. But we can think about something else. when we understand a lot of laws of nature, we notice that the life exists because there are many remarkable constellations happen in the different parameters. For instance, we heard about creation of chemical elements, and one of the important things is the creation of carbon. But creation of carbon enough to have life as we have it on Earth is only possible because there is fine-tuning between several different fundamental constants. This allows to have very special excited level of carbon nucleus, which is roughly equal to 3 energies of helium nucleus. If it's 5% out, some of the fundamental constants, we will not have enough carbon, and maybe this life will be impossible. There are quite a few other remarkable things about how nice fine-tuned things happening. And well, we can wonder, is it accident or special? Of course, there is like very scientific say anthropic principle. This means we are here to ask questions because fine-tuned exists. So let's say biophysics is about like result of anthropic principle. We are here to ask questions about theory of everything, and let's see how we organize as life and ask all these questions in physics. So I welcome to come for these 2 events. And finally, I would like to notice non-scientific part of this lectures. We organize this event to raise some funds in support of Ukrainian people. You can read why we are doing this on the website. And yeah, you can read there on the website. I do not want to discuss it here, but please do it. And thank you for coming, and hope you will come next time.
This one riding with an 8-legged horse.
So, who knows the name of the class? Slavery. Huh? And this is Schrodinger's path. Yeah. So this is Feynman diagram. This Feynman diagram. These are integrals, and here you cannot see it, but it's actually binary code. It's sequence of zeros and ones. Yeah, Odin is riding slave here. Yeah, straddling between different walls. Its main is made out of integrals. Yes. Yes, and it travels behind it's an artist's impression of a black hole. And we have some waves. You know, we have waves. I mean, everything is actually waves. So it's traveling the quantum field of the reality. So this is, yes. And Schrödinger can observe all that. Yes.